In this module, we will discuss impedance matching. Let us first look at the reasons for impedance matching. Why would one be interested in matching impedances? One of the reasons why we do impedance matching is to actually transfer maximum power. Now you know probably from your early circuits courses that if you consider a source, okay, so let's assume a sinusoidal source, or it could be any other source for that matter, which has a certain impedance, okay, because we are assuming sinusoidal excitation. So for that particular frequency there is a certain source impedance or generator impedance as it is called in the microwave and RF literature. So this is fixed, okay, so the Zg is fixed, and if we have an ability to choose the load impedance, okay, and this load impedance could be chosen at our will, then we can show by circuit analysis, or we have probably shown in the circuit analysis courses, you might remember from that one, that maximum power will be transferred across the load when the load impedance is chosen such that it is equal to the conjugate of the generator impedance, right. So this is the case where we can actually expect, or we actually have maximum power to be transferred to the load, okay. Of course there is a slightly thing which probably people don't realize, that if at all we just have a source which has no internal impedance, okay, so there is no internal impedance. Suppose we have situation where the load impedance is fixed and we are actually free to choose whatever the generator impedance we have for a given value of the source voltage Vs, then what is the generator impedance that you would choose in order to maximize power transfer across the load? Most people would say that, well, maximum power transfer cannot be wrong because ZL is equal to Zg complex conjugate is supposed to give you the maximum power, but they would actually be wrong. Maximum power transfer assumes that Zg is non-zero and it is fixed, and it is ZL which is being varied. If at all I have to choose a source whose internal impedance I can choose, something that you would not normally have, but if hypothetically I am able to choose the source with an internal impedance, I would actually set Zg is equal to 0. So this is not the condition that would maximize the power transfer to the load, but Zg is equal to 0 would actually correspond to the maximum power transfer, because simply there is no drop across Zg, okay. So this aspect of maximum power transfer should be emphasized, or I would like to emphasize that one. Basically what it says is that for a fixed Zg, okay, find ZL that maximizes power, okay, so that maximizes power transfer in this case would be ZL is equal to Zg complex conjugate, okay. So you don't normally encounter a situation where the load is fixed and you can actually vary the Zg component, I mean the source impedance, but there are additional equivalent methods of achieving the second result. Anyway, so going back to the maximum power transfer theorem or maximum power transfer idea, that is one of the primary reasons why we would like to impedance match. So if we can get this condition ZL is equal to Zg complex conjugate for a fixed generator impedance, then I will be able to transfer maximum power across ZL, and that is something that I would like. Suppose I have an antenna, okay, the antenna presents a certain equivalent load impedance, okay, so let's call that as some complex load ZL, and it is to be connected via a transmission line to the generator, okay. This is something that you would be doing in your labs if you were to perform some microwave experiments or antenna measurement experiments. You actually have an antenna, you have a cable, okay, so this cable, assume that it is lossless and is characterized by the characteristic impedance Z0, okay. So as I said, we will only assume lossless transmission lines in this course, okay. So for this lossless transmission line characterized by the characteristic impedance Z0, we obviously know that if the transmission line has a length L, in general ZL gets transformed by the impedance formula, and the input impedance Zin will not normally be equal to Zg complex conjugate, correct. So this is not normally equal. Of course in those rare occasions where this would happen, then it is good fortune and we will be able to satisfy maximum power transfer, but the power will be transferred across only to the transmission line, okay. So the equivalent impedance seen at this point will be the input impedance Zin, and if this gets matched to Zg, then maximum power is launched on the transmission line, but that same maximum power may not be delivered to the load because these two are not matched, right? So the general situation is that if you have these kind of scenarios, right, you want to actually put matching networks everywhere. So you actually put a matching network at the source side, or you do the impedance matching. Okay, so this is the match network that you have to put, so that maximum power is launched on the transmission line. And similarly on the load side you actually put a matching network so that you satisfy maximum power transfer theorem over here. So you actually transfer maximum power to the load. So you typically have a source matching network as well as a load matching network, all with the goal, same goal of maximizing power across the load. So you don't want any power to be wasted because of the reflections that would arise when the loads are not matched. So you understand that one, right? So if there is a generator impedance Zg, then that is, if that is not equal to Z0, there will be reflections at the source end. Similarly, when Z0 is not equal to ZL, there will be reflections at the load side, and these reflections would create power losses. Some energy will be stored in the transmission line in the form of reflected voltages and currents. So we don't want any power to be wasted in the transmission line because of this reflection problem. So that brings us to the next requirement for impedance matching. We want to impedance match to make SWR equal to unity. That is, we want to keep reflections to be 0. Okay. Now what happens if the reflection is not 0? If the reflection coefficient is not 0, then SWR will be greater than 1, and the input impedance that this source sees, at this particular point will actually depend on the transmission line Z0. It will also depend on the length of the cable. It will depend on the load. Suppose you have two antennas to perform measurements. When you are performing antenna pattern measurements, you will actually have a reference antenna as well as you will have an antenna under test which you are using. So if you have those two antennas, the impedances that they would present to the generator will be totally different if SWR on the line is not equal to 1. If SWR is greater than 1, losses increase. The input impedance seen depends on ZL as well as L. On the other hand, when SWR is unity, then the input impedance seen will be completely independent of the length of the cable. It would be equal to Z0. If SWR is almost equal to 1, remember SWR will always be greater than 1, but in the lower limit, if it is very very close to 1, then the input impedance seen will be very nearly equal to Z0 and independent of the load that you connect, and this is something that you want. Just because you change an antenna, you don't want to recalculate everything, or you don't want the efficiency to suffer, and if you want to avoid that one, you better put matching network such that there is no reflection at the source side, there is no reflection at the load side. Okay, so to avoid these reflections, or to make gamma L is equal to 0 or SWR is equal to unity, is another reason why we impedance match. If you go to active microwave devices, there are other reasons why you would try to impedance match. If you are trying to optimize the noise performance, okay, so you would actually try to optimize the noise figure. In this case, you would again perform impedance matches. Okay, so we have seen couple of reasons why impedance matching is important, but we have not really talked about how one can go ahead and perform impedance matching. So what does this matching network consist of? Suppose you assume that for some reason the antenna impedance happens to be about 100 ohms, okay, and I have a transmission line which may be just a 2-wire line which has a characteristic impedance of 50 ohm. Now if it was a low frequency application, if this was not really an antenna but some sort of an amplifier, then it would have been very easy for me to match them. What would I have done? I would actually have put a transformer and chosen the appropriate ratios of the turns of the transformer so that the impedance seen will actually be equal to. So I can transform this 100 ohm impedance to be looking as a 50 ohm impedance, and when I do that one, there won't be any reflections. So this is something that you can do only at low frequencies, right? Only at low frequencies I can transform this 100 ohm impedance into a 50 ohm impedance seen looking at this particular point. So this is one method. So transformer matching or matching networks using transformers, which is very widely or used to be very widely prevalent in the low frequency regime, is one approach. The other approach is to kind of mimic the transformer using a complicated networks of L's and C's. Okay, it turns out that a simple circuit such as this would be able to transform load impedances. Of course, there are various ways in which you have to arrange this one depending on the load and the characteristic impedance of the transmission line, whether which one is greater or which one is lesser. But the basic idea is that a network consisting of L's and C's is able to match or able to transform a load impedance onto Z0. Okay, so it can actually transform, if you were to put this, lumped element matching network, as we would call. So why do we call this lumped element? Because for frequencies up to say 1 gigahertz or slightly higher than that, the values that you obtain for the inductor and capacitor can actually be realized, even on a printed circuit board, can be realized using lumped elements. You can actually buy these inductors or capacitors and then place them at appropriate points on your matching network. Now that is obviously not going to work if your frequency goes beyond say 1 gigahertz. 1 gigahertz is already stretching it too much. So if you go beyond these frequencies, then lumped element matching networks are no longer the preferred choices, because you don't get an inductor to act like an inductor at high frequencies. An inductor actually acts like an RLC circuit. Okay, so this is how a typical inductor would look like. Probably the resistors should come in parallel, but that doesn't really matter. Similarly, a capacitor would also look like an RC circuit. There is an L part in that capacitor, the inductor part in the leads of the capacitor, but that can be usually neglected. But the point here is that lumped element matching network cannot be sustained at high frequencies, and if you are designing some microwave or radar applications or antenna applications at high frequencies, this is not the way to go for impedance matching. What can we do? There is an analogous transformer matching in transmission lines, using transmission lines, and this is called as quarter wave transformers. Okay, quarter wave transformer works on a very simple idea. Suppose I have a load impedance ZL connected to a transmission line of length L is equal to lambda by 4, having a characteristic impedance Z0. Okay, so in this case the input impedance seen, if this is the length L, the input impedance seen at the input terminals of the transmission line is actually equal to Z0 square by ZL. So if I were to match, so for example, if this Z in is supposed to be equal to ZG, okay, so if this ZG must be equal to Z in, then I should simply choose a characteristic impedance Z0 of a transmission line of length lambda by 4 such that this is equal to ZL into Zg. So choose a transmission line of length lambda by 4 at that particular operating frequency. To satisfy this condition, then any load which is typically real load to a typically real generator impedance. Okay, this is something that is usually used to match real impedances even at high frequencies. The problem here is that the bandwidth of this match is not very good, because it actually works only at a particular wavelength. For any other wavelength, the length will not be exactly equal to lambda by 4. For example, if you have performed all these designs with lambda of 3 centimeter, okay, and instead of sending in a nice sinusoidal signal at 3 centimeter, you actually end up sending a pulse like this. And we know that a pulse consists of multiple frequencies. So this is the frequency domain picture of this pulse, and you see that all these different frequencies would effectively be characterized also by different wavelengths. And if you have designed this one only for one particular wavelength, then which let us say is this wavelength, all the other wavelengths that are sitting here are not matched. So what would happen? There would be reflections at all these other points, and the pulse actually gets distorted. So the quarter wave transformer is typically used for sinusoidal steady state matching, but that cannot be used to match over a broad band of wavelengths, okay, such as something that you would find in a pulse. So what is the other option for us? There are additional options. One of them is known as stub matching, okay, and the number of elements that you use determines what kind of stub matching you are looking for. Again, the stubs could be series, okay, normally not used in printed circuit boards because it is very difficult to cut a part of the printed circuit board and insert a stub matching network there unless you design it at the beginning. Or you can use shunt stub matching, in which the stubs, which are the small open circuited or short circuited transmission lines, are called as stubs, and these stubs could be connected across in parallel or in shunt, or they could be connected in series with the transmission line and the load impedance, okay, in order to minimize reflections. Now this series stub is not widely used, so we are not going to discuss that one. In shunt stub, depending on the number of elements, you can have a single stub, only one stub placed at an appropriate location and chosen its length. You can have double stub, or you can have triple stub, or in general you can actually have a n stub matching network. Okay, the formulas and the procedures for this double, triple and n stub are quite complicated and not particularly suited at this level. So we will not look at double stub matching, we will only look at single stub matching, and we will look at stub matching in the shunt method. That is to say, we connect the single stub in parallel to the main transmission line. Okay, there are variations of this stub matching which actually exploit the non-uniform nature of transmission line. So far we have looked at transmission lines and we have drawn a generic circuit which consists of a uniform in a straight line and whose cross section is not changing. Right? Although in pictures I might not be able to show that one, the cross section taken at this plane on the transmission line, cross section taken at this plane on the transmission line would all look the same. Okay, so you take a coaxial cable and this would be the cross section of the coaxial cable for any length that you can choose. Okay, so at any point you cut and look at the cross section would remain the same. Such transmission lines are known as uniform transmission lines. Okay, but it is also possible to taper these transmission lines, okay, or exponentially increase, or you connect multiple sections of the transmission line. Okay, so you connect multiple sections of these transmission lines. Probably the figure did not come out very nice, but these different kinds of non-uniform transmission lines are quite widely used in microwave circuits in order to perform impedance matching because of their wide bandwidth characteristic and something that is required when you are transmitting pulses on a transmission line. So unfortunately we will not be able to deal with even these type of transmission line matching networks. So let us concentrate only on one type of transmission line matching network, which is the single stub matching network. So our goal is to consider single stub matching network. It's not really a network, it's just a single stub out there, but sometimes these matching networks were used in the earlier literature, so we just colloquially call this a single stub matching network. Okay, so the basic idea is this. So go slowly over here, understand the basic idea, the numerical examples will very easily follow. So let's begin by having a certain load ZL. Remember, we are not maximizing the power transfer, we are not choosing to impedance match in such a way that Zg complex conjugate is actually equal to ZL. We are not doing this. What we are trying to do is to minimize SWR on the line, which is slightly easier to perform. So we try to make ZL look like Z0 so that there is no reflections on that particular transmission line. And in case Zg also happens to be different from ZL, then we try to make Zg also look like Z0 so as to avoid reflections at the generator side. Okay. So this is the load. Okay, these leads are very short, assumed to be of ideally 0 length, so don't bother about these lengths. But to this load terminal, you connect a uniform lossless transmission line having a characteristic impedance of Z0. Okay, so you connect a transmission line having an impedance of Z0 of any length that you are considering. Now, if you go back to the impedance transformation formula, then you know that if the transmission line has a length L, then the input impedance seen at this point is given by one complicated formula, but on a Smith chart I can actually find out the input impedance given ZL, Z0 length and the operating wavelength of this particular network, right. So in general, of course, Z0 is not equal to ZL, therefore gamma L will be non-zero, but it is possible to rotate this ZL or transform this ZL to some Zin. Now if we were able to transform this ZL into a form which is useful for us, then we can talk about matching. Okay, so what do we do there? Before that, let us just put some convention. The main transmission line is the one which is connected to the load and upon which we are trying to minimize the reflection. So let us call this as main transmission line, main T line. Okay, now what we do here is that as you go through ZL, let's plot the corresponding Smith chart over here. Don't take the Smith chart too literally, this is just to give you an idea Okay, so I have this constant R and these X circles, correct? On the Smith chart I have all these constant circles. Now I also know that there is a unit circle on the Smith chart, right? On the unit circle, what are the impedances? The impedances on the unit circle are of the form 1 plus jx, correct? That is the impedance on that form. If I were to use this Smith chart as an admittance chart, then the admittance on the unit circle will be 1 plus jb. Okay, so with this unit circle in place, what we would like to do is to take any load which is described by a certain SWR circle, right, upon which this would actually be propagating. Since this color is not very nice, let me redraw this particular thing. Okay, so let me write the Smith charts in this way and write down all these constant X circles. Okay, let me write down the unit circle, that is the unit circle which I have drawn. Okay, and now this is the SWR circle. Okay, so this is the SWR circle. Upon at some particular point there is a load here. Okay, so this is the load point ZL which we have drawn, and of course I cannot actually plot ZL, but I will be plotting the normalized value of the load impedance. How do I obtain normalized values? By dividing ZL by Z0. Okay, now you look at this red curve, okay, which represents the constant SWR circle characterized by this ZL and Z0. Okay, any movement towards the generator, so as I move towards the generator, I look at this ZL bar and then I keep moving along the constant SWR circle. Now what happens at this point? At this point something interesting has happened. I am moving on the SWR circle, this is my constant SWR circle. What actually happened was I hit upon a unit circle, right? So I hit upon the unit circle on the Smith chart. So at this intersection point, okay, the SWR on the circle, as you keep moving, when it meets the unit circle, it indicates that the impedance at that distance from the transmission line is of the form 1 plus jx, correct? So this is what actually implies as you move along the constant SWR circle. So you meet the unit circle and the impedance at that point will be 1 plus jx. Okay, now this is what we have obtained so far. So what we had was a transmission line, you moved a certain distance on the transmission line so as to make this ZL or equivalently the admittance YL, okay, as 1 plus JB. Of course if you keep continuing, right, so you continue this movement on the SWR circle, you will actually reach a second intersection point. At that intersection point the impedance happens to be 1 minus JB or JB prime. Okay, it would be 1 minus JB prime. You can choose any of these as your possible solutions, as we will explain later. Usually you would try to find the first intersection to the unit circle. Okay, usually you try to find the first intersection to the unit circle. Call this as 1, call this as 2. So you are usually interested in where the SWR meets the unit circle for the first time. Okay, and read off the values of the admittance at that point. Now why am I talking of admittance? Because as I said, this is a single stub matching, but the stub will be connected in shunt. So it is better to deal with admittances rather than impedances. So ZL becomes YL. Of course it needs to be normalized, so therefore ZL bar actually becomes YL bar. We know how to do this one on the Smith chart already. And then you have actually moved a certain distance on the transmission line. Okay, so sorry, we used L here. So you have moved a certain length L on the transmission line, okay, so as to make the admittance out here, okay, some YL prime, let us call this one, looking into the transmission line terminals of the characteristic impedance Y0 to be equal to 1 plus JB, okay, where B is the normalized imaginary part of the admittance, but it is at least one step closer to matching. Why? Because you only now have to take out this JB. How do I take out this JB? Well, mathematically simply add something to this, let us call that as the stub admittance, such that the result is 1 plus J0, right. Now I already know what is this YL prime, which is the impedance or the admittance seen looking at a distance L, which is the point where the SWR circle has actually met the unit circle. So YL prime is 1 plus JB plus the stub impedance is equal to 1 plus J0, this obviously implies that the stub should be equal to minus JB. So in other words, the stub must be chosen such that its admittance is equal to minus JB. So when you choose that one and then put up the stub, you are ready to do the stub matching. Again, these impedances can be obtained. Remember, open circuited or short circuited transmission lines would always give you capacitive or inductive reactances, right? So it would always give you imaginary parts of the reactances. So you choose the length of this appropriately, so call this as say D. So you choose the length of this one appropriately. If D is chosen according to whatever the value of B required, then it is possible to either use a short circuited stub or an open circuited stub in order to provide an admittance seen looking into this terminal at the same plane as Y stub, so that the total admittance seen to the left of the stub, okay, would actually be equal to 1 plus J0, and the transmission line is actually matched and there won't be any reflections. Okay, so this is basically the idea. So let us try and put this idea into practice. Okay, so there is a small way in which I would like to show this one. I will not draw the complete Smith chart, but if you have the Smith chart with you, you can actually follow the idea over here. Okay, so let's say I have the load impedance. Okay, there is actually two steps in this Smith chart. The first step would be to determine the length to which you have to move along the main transmission line in order that you meet the unit circle. Once you have met the unit circle and read off the corresponding value of the admittance there, you need to consider whether it's a short circuit or an open circuited stub, and then move in such a way that you are actually be able to obtain minus JB. Okay, so that the total admittance actually adds up to 1. So let's say I have a ZL which is equal to 2.1 plus J.8. Okay, so on the Smith chart you can locate this one, and from ZL you can actually obtain YL. Okay, let's also assume that Z0 is there. Okay, so if you assume that Z0 is let's assume that this is about 50 ohms. Okay, so assume a characteristic impedance of 50 ohm. Oh sorry, this ZL I have already given you in the normalized form, so don't worry about what Z0 is, but remember this normalization has been done with respect to the main transmission line. Okay, Z0. Now with ZL bar you can actually obtain YL bar. Mathematically you can do that, but on a Smith chart it becomes easier. So let's go ahead and construct our Smith chart. This particular circle is my constant SWR circle. Okay, so this is the SWR circle with the load having a value of 2.1 plus J.8, and that should occur somewhere over here, right? So on the 2 circle, so this is where somewhere a 2 circle happens, and then this is 0.8. So let's say this is somewhere over here. So this is my load ZL bar, and how do I obtain the admittance YL bar? Why, on the SWR circle I have to move 180 degrees, which means I have to find the opposite point, okay, to obtain YL bar. So I have obtained YL bar on moving along the SWR circle. Okay, you can find out what is the SWR for this one, or if you assume that the SWR is given to you. Okay, so with the SWR circle, so let's assume, because for that one you still need some Z0. So assume that on the corresponding SWR you have actually moved 180 degrees, which means finding the diametrically opposite point, and that is where your YL bar is. So this is your starting point, right? So this is your starting point. Now you have to move a length L, or normalized to the wavelength L by lambda you have to move. To do that one, you also require where the unit circle is located, right? So let's say the unit circle is this particular circle. Okay, so this is my unit circle, and locate the unit circle. Okay, so now you start at this YL bar and you keep moving along the constant SWR circle until you hit the intersection to unit circle. Again you have two intersections, one at A. If you continue to move towards like this, you would move and intersect this unit circle at point B as well. Okay, we don't want to consider B, let us only consider point A. So at A you can read the value. So let's say this is about 1 plus J.95. Okay, so again this is not an exact value, this is something that you have to read it from your Smith chart. I am making some simple numbers over here just to show you how to perform this stub matching. Now what is this point A? Point A is the intersection of SWR and the unit circle. Where would they intersect? It is actually the corresponding length over which you have moved along the transmission line, right? Along the transmission line you have moved a distance L such that the admittance seen at this point is YL prime, right? So this is YL prime point. YL prime point is point A on the Smith chart. And how much distance have you moved? You can easily find out. Extend this to the outer periphery. Note down what is the WTG scale. On the WTG scale, note down the starting coordinates, and then at point A, so from the center of this one you go to point A and then extend that one, okay. On the outer WTG scale you note down what is the difference, and this length is actually the length that you have moved, okay. So this is the length along which you have moved in order to arrive at YL prime. So at YL prime we have seen that it is equal to 1 plus j 0.95 the admittance. Therefore the stub normalized admittance that you require in order to obtain impedance match is minus j 0.95. And on this stub network, where should I move towards? From the short circuit point I should be moving towards the generator, right, so that at a certain length d the stub admittance normalized will be equal to minus j 0.95. Now where is the short circuit located? Remember, if the Smith chart is being used as an admittance chart, short circuit is located here, okay, and open circuit is located over here. And after locating YL bar, from this point onwards we will treat the Smith chart as an admittance chart, okay. So since we are treating a chart as an admittance chart, the short circuit is located at this point. From this, on the short circuit, on the outer, the largest circle, you keep moving until you hit this point which presents minus j 0.95 admittance, okay. So this is the admittance that you would obtain when you move along the outer circle, on the circle of r equal to 0 or equivalently g equal to 0. The question is, why am I moving on the outer circle? Because what is the SWR for a shorted line or an open circuit line? The reflection coefficient magnitude is 1, therefore SWR on these lines is equal to infinity, right. So that would correspond to gamma L is equal to 1, right, and that is actually the outermost circle. So on the outermost circle you keep moving until you hit minus j 0.95, which is exactly required to cancel out this plus j 0.95, okay. How much distance you had to move? Again, from the center of the chart you note down, from the short circuited point you note down what is this length, okay. So this length will give you the stub length which is required in order to obtain an admittance which can be used to cancel the admittance obtained at point A, okay. So these are the two steps, finding L and finding D. Just to give you a summary, start with ZL, locate YL bar. Once you have located YL bar, you are now considering the Smith chart as an admittance chart. Move on the YL bar on the SWR circle until you meet the unit circle, okay. So that unit circle meeting happened at point A, okay. At this, read out the value of the impedance, read out the value of the admittance, and you find out what is the corresponding point that you need to cancel. So here you have 1 plus j 0.95 to cancel. So to cancel plus j 0.95 you need minus j 0.95. That you can obtain by starting at the short circuited point, because we are assuming that the stub is short circuited, and then moving on the outer periphery or on the outer circle, the largest circle, gamma L equal to 1 circle, until you reach the constant minus j 0.95 arc, okay. So from there, from the center you draw a line, extend, find out the distance. This is called single stub matching, okay. There is only one complication that might arise. For example, if someone specifies that I don't have the characteristic impedance of the stub equal to y0, let's say I have something which is y0 prime, how do I proceed to this problem? Nothing. You first do the first step as it is, locate ZL, go to YL bar, move on the SWR circle until you reach point A. Now what you have obtained is an admittance which is normalized with respect to y0. So you can actually first unnormalize, okay, multiply by y0 of the main transmission line. So therefore this becomes unnormalized impedance, okay. Once you have done that one, again normalize with respect to y0 prime, okay, not the real part, only the imaginary part, normalize with respect to y0 prime, okay. So by dividing by y0 prime you have normalized with respect to y0 prime, you take that as the imaginary part that you need to cancel, If it is plus, you add a minus. If it is minus, you make it plus, and then move along the new imaginary part value. Okay, so obtain the matching. So this brings us to the end of stub matching and impedance matching. In the next module, we are going to discuss time domain or transient analysis of transmission lines.